What specific problem does the temporal Gaussian hierarchy aim to solve in the context of volumetric video synthesis, and how does it address the limitations of existing methods?
The temporal Gaussian hierarchy aims to solve the problem of efficiently modeling long volumetric videos while maintaining low computational costs and high rendering quality. Existing methods struggle with significant GPU memory and time requirements that scale with video length, making them impractical for extensive sequences. The temporal Gaussian hierarchy addresses these limitations by employing a tree-like structure that organizes temporal segments of varying lengths, allowing for efficient identification of relevant segments for specific timestamps. This hierarchical approach reduces the number of 4D Gaussians needed for rendering, thus minimizing memory usage and ensuring constant GPU memory requirements regardless of video length. Additionally, it enables the model to effectively handle areas of dynamic scenes with different motion granularities, enhancing both training efficiency and rendering speed.
How does the proposed temporal Gaussian hierarchy work? Illustrate the methodology step by step, including its hierarchical structure and the use of 4D Gaussians.
The proposed temporal Gaussian hierarchy, TGH, operates through a multi-level hierarchical structure designed to efficiently model dynamic scenes with varying motion scales. First, the video is divided into segments of different lengths at each hierarchical level, where deeper levels represent shorter segments to capture fast motions, while higher levels accommodate longer segments for slower motions. Each segment contains a set of 4D Gaussians, which are defined by parameters such as means, scaling, opacity, and quaternions, allowing for a rich representation of the scene dynamics. The TGH structure ensures that the influence radius of the 4D Gaussians is appropriately covered by the segment length, preventing overlap with segments at finer levels. This design allows the model to maintain nearly constant memory usage and computational costs during training and rendering, regardless of the video length, by only loading relevant segments into GPU memory for processing at any given timestamp.
Can you provide a simple yet illustrative example to demonstrate the interactions between different levels of the temporal Gaussian hierarchy during video rendering?
An illustrative example of the interactions between different levels of the temporal Gaussian hierarchy during video rendering can be seen in a dynamic scene with both slow and fast-moving objects. For instance, consider a video of a park where a person is walking slowly in the background while a dog runs quickly in the foreground. In this scenario, the temporal Gaussian hierarchy would utilize longer segments at the coarser levels to represent the slowly changing background, effectively sharing Gaussian primitives across these segments to reduce model size. Conversely, at the finer levels, shorter segments would be employed to capture the rapid motion of the dog, ensuring that the rendering accurately reflects its dynamic behavior. When rendering a specific timestamp, the system identifies the relevant segments from both levels, allowing it to efficiently sample the appropriate 4D Gaussians that influence the scene at that moment, thus maintaining high rendering quality while optimizing memory usage. This hierarchical approach ensures that the rendering process is both efficient and capable of handling the complexities of dynamic scenes.
What are the key theoretical and practical benefits of using the temporal Gaussian hierarchy over previous methods like 3DGS and 4DGS, particularly in terms of efficiency and rendering quality?
The temporal Gaussian hierarchy, TGH, offers significant theoretical and practical advantages over previous methods like 3DGS and 4DGS, particularly in efficiency and rendering quality. The TGH utilizes a hierarchical structure that allows for the efficient management of temporal segments, enabling the model to maintain nearly constant GPU memory usage and computational costs, regardless of video length, which is a major limitation in 3DGS and 4DGS where resource requirements scale with video duration. Additionally, TGH effectively captures varying degrees of temporal redundancy by assigning different segment lengths to areas of slow and fast motion, which optimizes the representation and reduces the overall model size. In terms of rendering quality, TGH achieves superior results by leveraging a compact appearance model that minimizes storage overhead while preserving high fidelity in dynamic view synthesis. Experimental results demonstrate that TGH outperforms existing methods in both rendering speed and visual quality, achieving a rendering speed of 450 fps on an RTX 4090 GPU while handling extensive volumetric video data efficiently.
How is the temporal Gaussian hierarchy validated? Discuss the experimental design, datasets used, and the metrics for assessing its performance against existing approaches.
The temporal Gaussian hierarchy, TGH, is validated through a series of experiments using various datasets, including Neural 3DV, NeRF Outdoor, Mobile Stage, and a newly created dataset called SelfCap, which features long multi-view sequences ranging from 2 to 10 minutes. The experimental design involves comparing TGH against state-of-the-art baseline methods, such as 3DGS, 4DGS, and NeRF, focusing on metrics like PSNR, SSIM, and LPIPS to evaluate image quality, alongside VRAM usage, storage requirements, training time, and rendering speed. The results demonstrate that TGH significantly outperforms existing methods, achieving superior visual quality and rendering efficiency while maintaining lower training costs and memory usage. Specifically, TGH can handle long volumetric videos, processing up to 18,000 frames at 450 fps on an RTX 4090 GPU, showcasing its scalability and effectiveness in dynamic view synthesis. The ablation studies further confirm the advantages of TGH by analyzing its components and hyperparameters, illustrating its efficiency in managing GPU memory and computational costs during training and rendering.
What limitations or potential drawbacks does the temporal Gaussian hierarchy have, especially when dealing with long video sequences or highly dynamic scenes?
The temporal Gaussian hierarchy, while efficient for modeling long volumetric videos, does have some limitations. One potential drawback is that if the segment lengths are not optimally set, either too long or too short, it can lead to increased VRAM usage and slower iteration times due to the sampling of Gaussians that do not contribute to rendering at specific timestamps. Additionally, while the model maintains nearly constant memory costs, the hierarchical structure may introduce overhead in the sampling and update processes, particularly if too many levels are used, which can degrade iteration speed. Furthermore, the model's reliance on a tree-like structure to manage segments may struggle with very sudden motions in highly dynamic scenes, as the varying degrees of temporal redundancy might not be effectively captured. Lastly, the performance of the compact appearance model, which is designed to reduce storage costs, may compromise the ability to model view-dependent effects, if not carefully balanced, potentially affecting rendering quality in complex scenes.